Good morning to everyone. My name is B.keerthi from CSM Department, second year, studying at Srinivasa Ramanathan Institute of Technology. Today, my topic is about single source shortest path in general weight. Here is my topic, single source shortest path in general weight. Let's go on it. First one, introduction to single source shortest path. The single source shortest path problems aims to find the shortest path from the source vertex to all other vertex in the weighted graph. The weight of the edges can represent various constraints like a distance, time or cost. Understanding SSSP is a crucial for applications in networking, routing and geographical information systems. Graph representations. Graph representation can be using adjacent matrix or adjacent list. Each edges in the graph has a weight associated with it that can be positive, negative or zero. The choice of representations impact the efficiency of an algorithm used to solve the SSSP problems. Importance of an weight types. The types of weight in the graph influence which algorithm is the best suited for solving the SSSP problems. Positive weight typical allow the users of digestious algorithm for efficient computation. Negative weights necessity the users of an algorithm like Bellman-Ford which can handle the such cases. Digestious algorithm. Digestious algorithm is an efficient method for finding the shortest path in the graph with a non-negative weights. It is utilized as a priority queue to continuously extend the shortest path tree from the source's vertex. The time complexity of digestious algorithm of O, V plus E log of V, where V is the vertex and E is the edge. Digestious algorithm for non-negative weights. Algorithm type greedy uses a priority queue for efficient shortest path selection. Condition works only with a non-negative edges weights. Assumes shortest path does not change once selected. Algorithm steps initialization set distance to source as 0. All other nodes as vertex selection. Select the vertex with the smallest tentative distance. Relaxation update distance to neighbor if a shortest path is found. Time complexity using a mini priority queue. Limitations cannot handle the negative weights. Assume once a vertex is processed, no shortest path can be found to it, inapplicable for the graph and the negative cycles. Bellman-Ford algorithms. The Bellman-Ford algorithms can handle the graph with the negative weights and detect negative weight cycles. It works by iterating through all the edges and relaxing them repeatedly for a number of iterations equal to the number of vertices. Its time complexity is 0 of VE makes it less efficient than a digestious for dense graph with a non-negative weights. Algorithm steps. Initially the distance to source is set to 0 as other sets to. Edges relaxation for each vertex. Iterate over all the edges. Relax edges by updating distance value if a shortest path is found. Repeat times where is number of a vertex 3. Negative cycle detection. Check for the further relaxation after iteration. If any distance can still be reduced, a negative cycle exists. Time complexity 0 of B into E. Slower the digesters but no more vertices. Applications useful in the concurrence exchanges. Arbitrary detections under the network with various edge weights. Comparing digesters and the Bellman-Ford. Digestion algorithm advantages. Faster in non-negative graphs. Work well with a priority queues. Limitations cannot handle negative weights or detect negative cycles. Bellman-Ford algorithm advantages. Handle all the types of edges. Weights detects negative cycles. Limitations slower than digesters, especially in the dense graph. Uses cases. Digesters when all the edges weights are non-negative. Road networks. Bellman-Ford for a more general uses. Cases where weight might be negative. So digestion algorithm advantages. Efficiency for non-negative weights. Digestion algorithm is the very efficient for the graph with the non-negative weights, achieving the time complexity with the priority queuing. Widely used in the real world applications, ideal for applications like GPS navigations and network routing where the weights are non-negative. Greedy and the straightforward, simple to the implement with the greedy approach, expanding the shortest path, iterations and without needing all the edges to be relaxed repeatedly. Disadvantages. Incompatible with the negative weights. Digestions cannot handle graph with the negative weights as it is assumes once a path is demanded shortest, it cannot be shorted further. Cannot be detected negative cycle. It cannot detect or the handle negative weight cycles with can be leads to incorrect result if they are present. Higher compulsivity on the dense graph without priority queues. Without a priority queues, digestions or compulsivity makes it less efficient for the dense graph. Bellman Fraud algorithm advantages: handle general weights, works with the graphs containing the both positive and negative weights, make it vertical for the various types of applications. Second one, detect negative cycles. Bellman fraud can detect if a negative weight cycle exists and report it, which is essential in applications where such cycles would create the infinity loop 6. Dynamic programming approach ensures systematic relaxation of edge, making it reliable even if complex networks and the weights. Disadvantages: slower than digestions, with the time compulsivity of a Bellman fraud is generally slower than the digesters, especially in the large and dense graph. Second one, higher complexity of a large graphs. Iterating over all the edges time makes it computationally costly for graph with a large number of vertices and the edges. Limited uses in the non-negative graphs. When only non-negative graphs are involved, digesters is generally preferable in efficiency. Title: Search algorithm. The A search algorithm is another approach used in the primarily in the path finding and the graph transversal. Here is the graph search algorithm and path finding algorithm and random path finding algorithm. Applications of an SSSP. SSSP algorithms are used in navigation system to find the shortest route from the one location to another. They are also applied in the networking route protocols to efficiently manage data packet transmissions. Another applications include social network analysis where the distance represents the relationships among users. Challenges in the SSSP: handling the negative weight cycle poses a significant challenge as it can lead to infinity loops in the path finding. Large graph with a many vertices on the edges can lead to performance issues and increased computations time. Ensuring the accuracy of the shortest path in a dynamic graph where weights may changes is also a complex problem. Further traits in the SSSP algorithms: research in the ongoing into the improving the efficiency of SSSP algorithm for the larger scale graphs. Machine learning techniques are being explored to predict and optimize this path in the dynamic environment. There is a growth interest in the parallel and the distributed algorithm to relevant modern computing resources. Conclusion: the single source shortest path problem is fundamental in the graph theory and has a widely ranging application. Various algorithms exist to address different types of graphs and weights, each with their strengths and weaknesses. Understanding these algorithms and their applications can lead to more efficient solutions in the real world sensors. Thank you. Thank you for giving this opportunity, ma'am.